Today's lesson is Module 2, Topic 1, and Lesson 5, 2.1.5, Run It Up the Flagpole, Application of Similar Triangles. So we're going to start. This is on page 79, Module 2, 79 in your workbooks. So go ahead and complete the first 3 warm-up questions, and then pause the video before you do that, and then press play when your 3 questions are completed. All right, question 1 in the warm-up. Solve for the unknown in each pair of similar triangles. Since they are similar, I can set up corresponding side length ratios. Although they don't give you any angle measures or any vertices that are corresponding to one another, we can just assume that the orientation is the same on both. So that would mean 3 is to 4 as x is to 6. And then when we cross multiply, we'll get 18 equals 4x. Divide both sides by 4, and we get 4.5. Moving on to question 2. Looks like this is somewhat of a 90-degree angle, so that's going to help me figure out short leg, long leg, or hypotenuse, I should say. So let's see. The hypotenuse of the smaller triangle is x, and I can put that over the hypotenuse of the larger triangle, equals the other length 7 of the small triangle over 9 of the large triangle. So cross multiply and divide, and you will get 9x equals 105. And then when you divide both sides by 9, you're going to get approximately 11.7. Last one, question 3. So I prefer to separate my triangles out when they're overlapping each other. And then that helps me calculate the length of the larger triangle more accurately. So the bottom side of the small triangle is 5. The bottom side of the large triangle is not 3, it is 8, because you are adding all of the bottom, the segment of 5 and the 3-unit long segment. And then 4 is the length of my vertical segment of my smaller triangle, and x is the length of my vertical side of my larger triangle. So 5 is to 8 as 4 is to x. Cross multiply. 5x equals 32. So divide both sides by 5, and we get x equals 6.4. All right, moving on to the learning goals for today. We're going to identify similar triangles to calculate indirect measurements and use similarity to solve for unknown measurements, which we've already done quite a bit already. So you've used proportions that equate the corresponding side lengths of similar triangles to solve for unknown measurements. How can we use similar triangles to determine measurements in the real world that are difficult to measure directly? So getting started, this is on page 80 for you as you follow along in your workbook. Question 1 says, how would you measure the height of a flagpole? So think about it. I don't know, you could say a measuring tape. Maybe you're thinking a measuring tape is definitely not long enough, so maybe a rope. But we do know that it's going to be difficult to measure a flagpole because it is pretty tall. So how would you measure the height of a very tall building? This is even taller than a flagpole. So kind of think about it. Let's see. If I know that a building has 3 stories, maybe I could measure 1 story by using a measuring tape or a rope. And let's say it's 15 feet. And then I know that every story is the same. So that's one way that you could measure a tall building. Maybe measure 1 story, it's closest to you, and then multiply by however many stories there are. Question 3, you're standing outside on a beautiful day. Okay, this is cut off, so I'm going to read on my paper. The sky is clear and the sun is blazing. You are looking at your shadow and thinking about geometry. Draw a picture of yourself and your shadow. So I'm a really good artist, so nobody be jealous. So here's me. And then here would be my shadow. All right. Part B. What is the measure of the angle formed by you and your shadow? Explain your reasoning. So I'm going to scroll back up. So what's the angle between myself and my shadow if I use maybe blue so we can see this a little better? So if I'm standing perpendicular to the ground and my shadow is on the ground, it would only make sense that the angle formed between myself and my shadow would be 90 degrees. So 90 degrees, part B. Part C. Draw a line segment connecting the top of your head with the top of your shadow's head. What geometric figure is formed? Let's go back up. I'll use blue again from the top of my head to the top of my shadow's head. What geometric figure is created? Well, obviously this isn't elementary, so we're not asking you to know if that's a triangle, but more specifically, a right triangle is formed. So now it says, suppose you're standing outside at different times of the day and the length of your shadow changes due to the sun's position. Does the geometric figure formed by the line segment connecting your head with the top of your shadow's head change? Explain your reasoning. So if I go ahead and redraw two different scenarios. So here's me. This is the first time I went outside. And then later I go out. I don't change sizes. I hope not, at least. That would be weird. Let's say my shadow is like this now. So the question is, does the figure formed by the line segment connecting your head with the top of your shadow's head change at all? Well, if our shadow size changes, then definitely the geometric figure would change. They are both still right triangles, but one is larger than the other.